not the others.
Sorry. All right. Hi. We are the Grill's UAV digital engineering team, and this is our project. First, we're going to introduce ourselves. So I'm Alex Hooper. I am a second-year Wright Scholar here at the Grill, and our team lead requested that we say our preferred hacker fuel. So for me, that would be water.
Hello everyone, my name is Amrit Kula. I am a first-year Wright Scholar and a freshman at Purdue University going into aerospace engineering. And my preferred hacker fuel definitely has to be Chips Ahoy Chewy.
Good morning, my name is Brad Sisk. This is my first year as a Wright Scholar, and I will be a rising senior at Waynesville High School. And my preferred hacker fuel is Chips Ahoy Chunky.
Good morning. I was a Wright Scholar last year. I'm an intern here at the Grill. My name is Ashton. I'm a rising sophomore at the University of Michigan studying aerospace engineering, and my preferred hacker fuel would be trail mix.
So for a brief overview of this presentation, we will be introducing our client and the challenge problem they had for us. We will go over a key element that this entire project runs on, nicely named software in the loop. We will then dive more into detail about individual components such as the sensors on the drone, the 3D environment, the logging system, and the artificial intelligence used in this project. We will then show a demo video and be happy to answer any questions you might have.
Next slide, please. So we'd like to introduce our client, Ken Sewell. He works at the Air Force Research Laboratory with the Summer of Innovation at the Wright-Brothers Institute. And one of his main objectives for this project was to evaluate and analyze human-machine interfacing, or the way that drones and people work together. For example, we want to see if a drone is more effective at our challenge problem with a pre-programmed flight path versus being completely user-controlled. Along with that, he wants to establish the ideal payload for a drone. So there are multiple different kinds of sensors, anything from speakers to thermal cameras that we can put on a drone. And we want to see what the most effective way to find a person is this summer. So the last objective was to determine the effectiveness of simulation training versus in the field training. And that mainly has to do with something the Air Force likes to call digital engineering. So at the Wright-Brothers Institute, they have what we call the physical twin, or a Aurelia X6 standard drone. Here at the Grill, we are the digital twin, where we've created a completely digitized environment of the drone and its search pattern and everything that goes along with our simulation. And we'll like to talk about the actual challenge problem in our search and rescue scenario.
Yeah, so for a brief overview of our challenge problem, our client basically asked us to simulate a search and rescue operation. Now, for that, we have the Aurelia X6 standard, which is the physical drone our client has. Now, as Ashton mentioned, we're actually working with a digital version of that, but let's concentrate on the physical one for a bit. The Aurelia X6 standard is a hexacopter with 6 rotors. Now, most of the drones we see on the consumer market are quadcopters, or 4-rotor drones. But the client chose a hexacopter mainly for flexibility. With a hexacopter, you have more freedom to decide what payloads you're going to mount and how you're going to mount them. And that becomes extremely important to a search and rescue environment, where testing different sensors or speakers or flashlights can either increase or decrease your search times. So that's basically what we're testing here. In addition to that, a search and rescue operation needs someone who's being searched for and rescued. And to model that, we have a model human with artificial intelligence built in. Now what this does for us is our human can basically model the exact or roughly exact movements that an actual person might exhibit out in an environment out in the real world. And when you're testing your methods for search and rescue, this becomes extremely important because it can tell you which methods are more likely to result in a faster discovery of your person. And one thing that our client requested is that all of our flight inputs be through a ground control software called Q Ground Control, which we'll discuss more in a bit. And an important component of this project is our use of IR or thermal cameras. Now, IR cameras just in general can really help you in a search and rescue scenario when you're looking for someone in a particularly difficult or foresty or woody environment. They can really speed up search times. And that can actually increase survivability. So So now discussing software in the loop. So Brad mentioned this earlier, and it's hard to understate how important this is for a project. So at its core, software in the loop is just the integration of hardware, firmware, and software in a completely virtual and software-based environment. So basically what we're saying is we're taking a physical drone, the firmware that's on the drone, and any software that runs it, and just modeling it all in software. For us, that really comes through 3 different pieces of software. From the bottom, we start at Q Ground Control, which is our ground control software. Out in the field, you might see a pilot fly a drone with a physical handheld controller. And basically, that's exactly what Q Ground Control does. We input flight commands here, we tell the drone to go to a specific location, change its altitude. It's all done through Q Ground Control. Now, the commands we put into Q Ground Control actually get sent to ArduPilot, which is the actual firmware that runs on our drone. Now, ArduPilot basically acts as a communicator between Q Ground Control, what we tell the drone to do, and AirSim, what the drone actually does. Now, AirSim is a flight plugin for Unreal Engine, and it models all of our flight physics, and it can model different weather conditions like wind, rain, and it can have our hexacopter react accordingly. So, as I mentioned earlier, a very important idea when you're using software in the loop is virtual testing. With virtual testing, when you're looking to test different payloads, like speakers, lights, sensors, cameras, out in the field that takes a lot of time and a lot of money. But here, we can basically do it for very little. We can basically buy a plugin or a sensor and just mount it on our drone virtually and test it. In the end, our client decided to settle on 2 different types of sensors. One being just normal digital cameras, and the other being IR or thermal cameras. Now, the more interesting of these 2 are the IR cameras, because in a virtual environment, nothing emits heat. So the way we do thermal cameras is through something called post-processing, which is basically where you take an image of a landscape and you apply a filter over it. There you can decide what's going to be blue or cold, so trees, the sky, roads, etc., and what's going to be hot or red, so your hiker, animals, things like that. Now, Unreal Engine often comes with its bugs when you're implementing new things. You can end up with a virtual game of the floor is lava, as you see over there. But after you sort out all those bugs, you end up with an extremely powerful tool for search and rescue, which, if your hiker is lost in super dense trees or in a valley, it can really help you pick them out and increase their survivability.
So something our customer wanted was a way to go back and see the results of a simulation for research purposes. So what they wanted was a CSV file with the start time of the simulation, the end time of the simulation, a heartbeat, which is just a generic information dump every 5 seconds with like the location of the drone, the time, and everything else. And then also whenever the hiker is visible. This was not easy to do. Unreal Engine doesn't have a built-in way to see if something is within the view of a camera. So what we ended up coming up with is the formula that you see in the top right there. That gives us a relatively good estimation of how much of the screen the hiker is taking up at any given moment, assuming there are no obstructions in the field of view. However, in the simulation, there are trees, there are cliffs, there will be obstructions in the field of view. So we have to account for that. So what we do is we take multiple points on the hiker, or in this case, Leonard the Egg, our mascot, and we shoot little rays at it. And these rays will see what it hits before it gets to the target. If those rays hit nothing but the target, if all of them hit it, then we know it's 100% visible. But if only like 50% of them hit it, then we know it's only 50% visible. Then we take that, deduct it from the percentage that we got earlier, and that gives us a really good estimate as to how much they are actually visible. Then we log that for future reference and statistical analysis.
So for the 3D environment the drone would be flying in, as per our customer's request, we were to create a fall scene of John Bryan State Park in Yellow Springs, Ohio. So through open source elevation data through the United States Geological Survey, we were able to take that elevation data and import that into Unreal using the Terraform Pro plugin as a 2.8 square kilometer landscape. And then through the QGIS application, we are able to take the roads, trails, streams, etc., and import that onto the landscape in its real-life location. So as Amaranth and Alex mentioned earlier, Unreal is not always the nicest to work with, as we see in the one example being in the bottom right. All of the collisions were offset by quite a margin, as you see by my floating character and the floating trees. But eventually these bugs got sorted out and we ended with a finished, polished landscape.
In this landscape, we needed a hiker to wander around for a search and rescue scenario. And in order to have completely unbiased research, where the hiker isn't going to the same spot every time or traveling on the same path every time, we decided to have him be artificial intelligence, where he will individually pick out a random spot within a navigable area to move to. There are different kinds of behavior trees that he can move around for different kinds of search and rescue scenarios. One could be a lost criminal who is evading the drone, not trying to be found. There's other behavior trees such as wandering at random, or more for a hiker with dementia, where they may wander around a certain area of the park, but not completely at random, and follow more of a waypoint path. As well as that, we have, as Amber mentioned earlier, woodland creatures that have heat signatures. In a realistic simulation, we don't want the hiker to be the only living thing in the entire map. So we have deer and other woodland creatures that have an assigned heat signature. So that way, we can have false targets for the drone to seek out. We started with this pink hiker because he stood out really nice against our winter map, but then we eventually transitioned to this very realistic environment with a realistic hiker who's artificial intelligence.
So this is our demo video. On the right there, you can see Q ground control. On the left, you can see the simulation. And that blue box in the middle is the thermal camera. There's no heat signature to pick up, so that's why it's all blue right now. In Q ground control, you can see we're clicking a spot, and we set go to this destination. In just a second there. And the drone will do exactly that. And as it flies along, you'll see that there are some deer that it'll pick up on thermal camera. Right there on the left. And then finally, there's the hiker right over there, just walking around aimlessly. It's a very good simulation of the hiker. So that concludes the presentation for the most part. But first, we'd like to say thank you to everyone, and also lessons learned. For me, my biggest lesson learned is it doesn't matter if you've been coding basically every single day for the past 3.5 years, you can still reach a point of knowing absolutely nothing about what you're doing, and you can still overcome it.
My lessons learned would definitely have to be the value of perseverance. Over the course of the summer, we crashed our simulation 206 times, and we completely fried one of our computers. But in the end, we have a polished simulation to show for it, and we're proud of how far we've come.
I learned how to effectively communicate within a team and the importance of team camaraderie.
And I learned also how to effectively communicate with people on base as well as here, and more of the project management type of role. And we'd like to give a special thanks to all the people listed here. First, Mr. Tim Rodabaugh for being our mentor, Mr. Jack Hugh for all of his assistance this summer, Lieutenant Kyle Bucklew for his program management, Dr. Wink Bennett for starting the grill and doing everything since, and Mr. Ken Sewell for introducing this challenge problem for us this summer, and finally, Mrs. Deborah Miller for organizing the Wright Scholar Program this summer. This concludes our out briefing. Are there any questions?